Hello, this is Jack Bartman. This is a presentation for CareerFoundry about the study for the Organization of Climate Winds, studying weather conditions and climate change in Europe. The goals of this study are to identify weather patterns that are not normal for Europe, determine if those weather patterns are increasing, project future weather conditions for the next 25 to 50 years, determine the safest areas to live in Europe for the next 25 to 50 years. The machine learning options that we've studied over the last several weeks include a random forest, which has the strength of predicting weather anomalies and identifying key factors and data sets that are associated with certain climate conditions. The CNN-RNN, which is a deep learning for complex weather, which can be used for deep learning for complex weather interactions, using CNN to detect patterns in satellite images and radar data, and using RNN to detect patterns in historical weather data. And the GAN, the generative adversarial networks, can be used for image recognition to identify weather patterns, and also can be used to generate possible future weather scenarios, simulating data and creating synthetic data that can be used to study future conditions. So we'll be doing 3 thought experiments how to best utilize these tools. One is to detect unusual weather patterns. The second is to project trends in weather patterns. The third is to assess future scenarios for long-term weather change by location. For thought experiment 1, we will be concentrating on detecting unusual weather patterns. So the goal is to detect and classify unusual weather events such as storms and floods using satellite imagery and historical weather data. So the approach is to use RNN to analyze historical time series weather data to understand the sequences leading up to unusual weather events and improve classification accuracy, and extract weather features such as temperature and humidity from the historical data and train a random forest model to classify weather events based on these features, and then use a GAN to analyze satellite imagery and identify visual patterns associated with severe weather events. So to do that, we'll need high resolution satellite images of weather phenomenon, historical weather data sets with labels for various weather events, and try to find specific events leading up to unusual weather. A data bias may be that satellite imagery may not be represented for all geographic areas, resulting in an underrepresentation of certain weather events. The pros and cons of thought experiment 1. Random forests are very effective at reviewing data sets and selecting criteria to study what makes weather severe. The RNNs are good at reviewing historical data to understand the precursors to severe weather. The GANs are useful in pattern recognition for historical imagery for use in identifying weather conditions. For the cons, there can be some complexity in using multiple models and properly transferring the information from one model to the other. The GAN's ability to do proper pattern research is going to be reliant on the ability to access the vast database of historical weather images. Thought experiment 2. The goal is to assess climate risk across the different regions of Europe by integrating image analysis, historical data, and predictive modeling. The approach is to use GAN to process satellite imagery for real-time identification of climate risks such as drought areas and flood zones. We'll train a random forest model on regional historical weather data and combine that with CNN outputs to classify areas based on climate risk, and then implement an RNN to predict future climate risk based on historical trends, considering the impact of temporal weather changes. The data needed: historical images showing land use and weather impacts, historical weather data sets for different European regions, and climate risk assessments, data and impact data such as flood and drought occurrences. Data bias. Historical data sets may underrepresent certain geographic areas, and this could skew the model results. Pros and cons of this approach. The pros, the method will combine models of weather imagery and historic data to provide a robust framework against which to compare current conditions. The GANs can be used to evaluate real-time weather images to identify the precursors to severe weather events. The cons, multiple models may be needed to across different geographic regions to be accurate. There's the complexity of integrating different data sets and different models to produce reliable results. Thought experiment 3, to assess future scenarios for long-term weather conditions by location. The goal is to simulate the impact of weather change on weather patterns and assess the future scenarios for specific locations. The approach is to use GAN to generate synthetic weather data under different climate change scenarios, such as a change in temperatures, precipitation, wind, etc. Train RNN on both real and GAN generated data to forecast future weather conditions, focusing on key variables affecting climate change. Analyze which generated scenario most significantly affects weather patterns using random forest, identify critical variables, and thresholds for adaptation strategies. The data needed: comprehensive historical weather data sets and weather imagery. The data bias. The GAN-generated synthetic data may perpetuate biases present in the historical data, resulting in unrealistic climate scenario simulations. Additionally, historic weather data may lack sufficient representation of extreme climate events, resulting in gaps in the understanding of future impacts and the necessary adaptation strategies. Pros and cons. Pros: the GAN can produce synthetic data that can be used to project historical data into the future. The RNNs can use this synthetic data and compare it to the historical data to identify future trends in the climate for future geographic regions. The cons: multiple models may be needed across different geographic regions to be accurate. There is a complexity of integration for the different data sets and different models to produce reliable results. Summary. Thought experiment 1. Detect unusual weather patterns. This approach has a strong use of GAN's image recognition capability and RNN's review of historical data. It faces challenges using multiple models. Thought experiment 2. Project trends into weather patterns. This method is robust as it combines models using historical weather imagery and historical data to identify patterns that can then be used to compare to real-time information and create actionable information. It is likely to require many models to accommodate variations between geographic regions. Thought experiment 3. Access future scenarios for long-term weather changes by location. This method is the most interesting in some ways, as it uses machine learning to project synthetic data into the future and then do an analysis on that. It has several challenges, as extrapolating data is always questionable, and the complexity and number of the models needed to develop useful information over a large and varied geographic area may be challenging. Recommendations. Thought experiment 3 is the most interesting, as it shows the most potential to reach beyond what is common in modern meteorology. It is to best meet the organizational goals of climate winds and to provide information beyond the immediate forecasting. The recommendation is that all approaches have value, but the ability to do future projections using Thought Experiment 3 is the best use of limited resources. So thank you. Once again, I'm Jack Bartman, and you can follow up with any questions and my email is attached if you'd like to contact me.